Hello, everybody, and welcome to the Morrison Planetarium. My name is Katie. I use she, her pronouns, and I'm in the booth behind you. I am going to be taking you on our tour of the universe today. Throughout most of human history, humans have only had one tool to study the cosmos, our eyes. These days, we use gravitational wave detectors, rovers, probes, and telescopes both on the ground and in space to explore our universe. The program we're going to use for our tour, OpenSpace, uses all of the most up-to-date data from these different tools we have. In fact, we're going to see Earth as it was yesterday. This program is also open source, so if you like it, you can go home and download it onto your own computer. Before we start, I have a few housekeeping announcements. First, please turn off or silence all electronic devices, especially those cell phones. Keep them tucked away for the duration of the show. It's going to get pretty dark in here, and any excess light is going to be a distraction to those around you and ruin all the hard work your eyes have done adjusting to the darkness. There's also no filming or photography during the show. There's no eating or drinking in the planetarium, and this does include water bottles. And please be sure to keep your mask over your nose and mouth at all times. Thank you so much for doing your part to help keep everybody safe and healthy. Speaking of safety, we ask that you remain seated for the duration of the show. Again, it's going to get pretty dark in here, and these stairs can be difficult to climb. We also don't want you blocking one of our projectors and creating a U-shaped hole in the universe. If for some reason you do need to leave during the show, please exit to the top of the stairs. Go up, not down. If at any time you feel any of the symptoms of motion sickness, such as nausea or dizziness, we recommend that you sit back, close your eyes, remind yourself that you are sitting in a stationary theater and not flying through space, and the feeling should pass. All right, with all that said, it's now time to sit back, relax, and enjoy our tour of the universe. We are going to start our tour at a pretty familiar place, right here at home, planet Earth. This is where almost all of human history has occurred, and where all human beings live. Well, almost all human beings. At any given time, astronauts from countries all around the world are aboard the International Space Station, living and working together. The International Space Station orbits at only 225 miles above the Earth. So that's this distance here between the Earth and this yellow line. And it circles our planet once every 90 minutes. That means that it's traveling at over 17,000 miles per hour. And this is the part where I make a bad joke. I wouldn't want to have to pay that speeding ticket. Now, this is the International Space Station's orbit is the furthest that humans currently travel into space, but it's not the furthest we've ever been. Between 1969 and 1972, human beings went to the moon. 12 NASA astronauts even got to walk on its surface. So let's go take a trip over to the moon. The moon is Earth's only natural satellite. A satellite is an object that's orbiting a planet, and we've got a lot of things orbiting our planet, from GPS and weather satellites to the International Space Station. But the moon's the only one that we didn't put there ourselves. And here it is the moon. I'm going to turn the nighttime off so that we can see it better. But half of the moon is lit and half is always dark, because the moon rotates, so it gets night and day like we have here on Earth. So the half that's lit and the half that's dark is always changing. So to misquote Pink Floyd, there is no dark side of the moon really. Matter of fact, half of it is dark at any given time, and that half's always changing. This is the half we always see from the Earth, the near side of the moon. The reason we only ever see this side is because the moon is tidally locked to the Earth, meaning that the rate at which it rotates about its axis, so the length of a day on the moon, is equal to the speed at which it orbits around the Earth. Because of this, only one side of the moon ever faces the Earth. It wasn't until 1959 that human beings ever got to see what the far side of the moon looks like, when the Soviet Union sent a mission to go take pictures of it. And here is the far side of the moon. It kind of blows my mind that until very recently, humans just didn't know what this looked like. We could see it's very different from the near side of the moon. The near side of the moon has those dark, smooth plains called mare. The plural is maria, which means sea in Latin, because astronomers back in the day thought there might be bodies of water like our oceans here on Earth. But we know now that they're actually ancient lava plains from lava erupting from below the surface of the moon and filling in all of the craters on the near side of the moon. The far side of the moon has all of its craters still. We can see its craters because there was no lava flow on this side to fill them in, and there's no weather on the moon because it has no atmosphere. It has a very, very, very thin atmosphere. So there's no weather to change the surface of the moon. So this side has remained intact. It gives us not only a history of the moon itself, but a history of our whole solar system. We can study these craters and see what conditions were like at different periods in the history of our solar system. So the moon is 240,000 miles away from Earth, and it took those Apollo astronauts over 3 days to get to the moon, traveling at 25,000 miles per hour. Now we're starting to get to speeds and distances that are hard to imagine. So let's switch to a more useful unit of measurement. One of the ways astronomers describe distances is in light years, light minutes, light seconds. It tells us how far light, the fastest thing in the universe, travels in that given unit of time. The moon is 1.3 light seconds from Earth, meaning it takes 1.3 seconds for light that reflects off the moon to reach Earth. It also means that when you look up at the moon, you're seeing it as it was 1.3 seconds ago. Now, that's an important thing to keep in mind as we start looking at more and more distant objects. The further away something is from us, the further into the past we are seeing it. We never see anything as it is in the present. Now, the moon may be the farthest that humans have been, but we've sent robots like rovers, probes, and landers even further. So now we are moving beyond the realm of Earth and out into the solar system. At the center of our solar system is our star, the sun, which is about 8 light minutes away, or 93 million miles. Our sun is a middle-aged star at about 4 billion years old. Orbiting around the sun, we have 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now, you might be asking yourself, what about Pluto? Why didn't you mention Pluto? It's my favorite planet. Pluto was reclassified as a dwarf planet some years back, and for good reason, I think. So let's see some of the things that make it different from the 8 major planets. Let's look just at its orbit. So now I've put up on the screen Pluto's orbit, which is sort of a lighter blue color. And if we tilt the solar system the right way, we're going to see that Pluto's orbit, the plane of its orbit, is tilted with respect to the other planets. All of the major planets orbit within the same plane. If I put them on a table, they would all lie flat. Pluto's orbit, though, is tilted. It wouldn't lie flat on that surface. We can also see that it's more elliptical than the orbits of the planets. The major planets, their orbits are almost perfect circles. They're not quite circles, but almost. Pluto's orbit is much more egg-shaped. And in fact, over here, in some places, and crosses between Neptune and the Sun. It gets closer to the Sun than Neptune is. So it's not staying in its own lane. It turns out Pluto fits in a lot better with these objects. These are the trails of the trans-Neptunian object, or Kuiper Belt objects. These are small icy bodies like comets and dwarf planets orbiting the Sun beyond Neptune's orbit. In recent years, we've discovered some dwarf planets like Eris that are even bigger than Pluto. So I think Pluto is happy with its new classification. Instead of being the smallest planet in the solar system, it's everybody's favorite dwarf planet. And being a dwarf planet doesn't mean it's not worth studying. In fact, we have learned a lot of really fascinating things about Pluto from the New Horizons spacecraft. It took New Horizons 9 years to travel from Earth to Pluto. So speaking of New Horizons, let's see how far human-made objects have traveled out into space. New Horizons was launched in 2006, reached Pluto in 2015, and has been traveling through the outer reaches of the solar system ever since. In the 1970s, we launched Pioneers 10 and 11 and Voyagers 1 and 2 to take pictures of the gas giant planets. They are all traveling fast enough to escape the Sun's gravity and leave the solar system behind. Now, even though they've been traveling for about 50 years, Voyager 1, which has traveled the farthest, still hasn't traveled as far as light makes it in 1 day. So now let's leave our solar system behind and travel out into what's called interstellar space, the space between the stars. The nearest star, Proxima Centauri, is 4 light years away. So compare that to the 1 light day that Voyager 1 has traveled. So now I'm going to turn on something called the radiosphere. Now this isn't an actual thing you would see if you were to travel out this far into space. It's a representation of the furthest distance that human influence can be felt. In the 1930s, humans started emitting strong electromagnetic radiation in the form of radio waves, TV and radar signals, and atomic weapons detonations. These signals were strong enough to leave Earth. They travel at the speed of light, which means that the earliest signals have traveled about 90 light years. So that's the radius of the sphere here, 90 light years. Maybe someone out there has detected our signals, but where could that someone be? These markers I just put up represent stars where we've discovered an exoplanet. An exoplanet is a planet that's orbiting a star other than the Sun. The ones within the radiosphere are the only ones that have had a chance of detecting our radio signals. But there are so many more beyond that. Astronomers now believe that most stars have planets orbiting around them, making our solar system the rule and not the exception it once was. In fact, I just saw an announcement that we now have over 5,000 confirmed exoplanets. One of the big topics of research these days is finding Earth-like planets with suitable conditions for life. We wouldn't be able to travel to these planets since it would take more than 1 lifetime to get there, but it's nice to know that they're out there. and it helps us learn more about our universe. Now let's go beyond our stellar neighborhood and see what lies outside of it. Our little solar system lives in one of the spiral arms of the Milky Way galaxy. This is a computer model of what we think our galaxy looks like from the outside. We can't take an actual picture of it since we haven't left our galaxy, we haven't traveled this far, but we can use our observations to get a pretty good picture of what we think it should look like. We also compare it to our observations of other galaxies. The Milky Way galaxy contains more than 300 billion stars, which means there are likely billions of planets out there. It's 130,000 light years across. The amount of time it takes for light to travel from one end to the other is equal to the length of the history of the human species. But that's just our own galaxy. 2 million light years away is the Andromeda galaxy, our nearest major galactic neighbor. We've got some dwarf galaxies closer to the Milky Way, in fact, orbiting the Milky Way. But the Andromeda galaxy is our nearest big galaxy. The Milky Way and Andromeda are actually hurtling towards each other and will collide in about 5 billion years, creating a new combined galaxy nicknamed Milkdromeda. And I didn't make that up, that is what they are calling it. You don't have to worry about this collision, though. Galaxies are mostly empty space, so there isn't much risk of our solar system colliding with another star. Also, life on Earth will likely have already ceased to exist by then because of the sun's increasing temperature in its old age. The Milky Way and Andromeda galaxies are only two of the many hundreds of billions of galaxies that comprise the known universe. As we zoom out, all the dots you're seeing represent not stars, but galaxies, each containing hundreds of billions of stars. Galaxies aren't evenly spaced. They tend to cluster together in groups. Andromeda and the Milky Way are part of what we call the local group, which in turn is part of a bigger cluster called the Virgo supercluster. So, I have to make one note about the data we're seeing here. So these data points we're seeing come from all different kinds of galaxy surveys that have been done trying to map out our observable universe. And the way it looks, this bow tie shape here, or hourglass, it kind of makes it look like that the Earth is at the center of the universe. And that is not the case. There actually is no center of the universe. But Earth is at the center of our own observable universe because we can only look so far in any direction. We are at the center of a sphere that we can see. We've also got these dark patches here where it looks like we've got missing data, and that's because we can't really see very well in those directions. The gas and dust of the disk of the Milky Way is blocking our view. So hopefully someday we will have the technology to peer through the gas and dust and get a complete map. But with what we know about the universe and what we've observed in other directions, we are pretty certain that what's in these dark spaces here looks a lot like what we see in all the other directions. All right, let's move out even further. So now we're going to start seeing some red dots in our data, and these represent quasars. Another name for a quasar is active galactic nucleus. These are the cores of young galaxies, where gas is falling into the central black hole and extremely energetic electromagnetic radiation is being released. These are all billions of light years away, meaning they existed in the earliest stage of the universe when galaxies were just beginning to form. I like to think of them as the angsty teens of the universe. If we could see what they look like right now, they might look a lot like our own galaxy, but we'll have to wait another couple billion years to see that. All right, so now we're going to zoom out as far as we can go. There we go, those are quasars, and there we go. What we are looking at now is called the cosmic microwave background. It's basically the universe's baby picture. Isn't it cute? This light was emitted about 380,000 years after the Big Bang, which happened about 13.8 billion years ago. This is an image we get using radio telescopes. It's a temperature map. On average, this radiation currently has a temperature of about 2.7 Kelvin, which is equivalent to minus 455 degrees Fahrenheit or minus 270 degrees Celsius. But when it first emitted, it was much, much hotter. Because of the expansion of the universe, space itself is stretching, and that stretches the wavelengths of the light we see to a much cooler temperature. A 2.7 Kelvin is the average temperature, but there are actually little tiny fluctuations. Brighter areas are hotter, denser regions, and darker areas are cooler regions. Cosmologists use those fluctuations to learn about how the earliest structures of the universe formed. This radiation comes from all directions all at once, but don't worry, it's not dangerous. If you've ever seen static on an old television, some of that static is coming from the cosmic microwave background. So this is as far as we go. There's no light to see past this point. If we want to directly observe anything older than this, we'll have to use some other method of observation. So for now, let's head home. As a planetarium presenter, people often ask me what my favorite planet is, and I give them what seems like a boring answer: Earth. Humans are perfectly suited for Earth. It provides air that we can breathe, water we can drink. Its atmosphere protects us from harmful radiation from the sun. It provides trees whose shade we can sit under, flowers for us to smell, cats to pet, and dogs to play with. In the scheme of things, it may seem like a small, meaningless speck of dust, but to us, it's our only home. So when you next look up at the night sky and think about the vastness of space, I hope you remember just how special our home truly is. All right, and that's our show. Thank you so much for joining us.